All right, so we are in that lovely after the exam review time, and we're going to do 2 follow-up questions. I'm actually going to start with the exam question first, which is not normal for me, but that is because this is shorter. So plus I can show you a little something else. So I think bang for your minute. This is better. Okay, so it says, so the question was about 26 and getting the correct answer on this one. Determine the concentration of sulfite in a 0.255 molar solution. You have Ka1 and Ka2. This is the closest thing to a trick question we actually ever give you, because essentially this is asking you about a diprotic acid. So you're going to lose first 1 proton, and then the other proton, and you lose these sequentially. And you can do the ice table out, and that's probably what you did. You probably went ahead and did 2 ice tables, but you don't have to, because we teach in class, we teach in the notes, and I will actually show you a video where I did this, that Ka2 is equal to that concentration. So the answer is just B. Ka2 should be the answer to this question, and you're done. And that's it, and it's over. And there's absolutely no math required for this problem. For those of you that are like, but what about my ice table? What I'm going to do, instead of walking you guys through all of that math, is I'm going to show you where you can find it. Yes, so I am in Microsoft Teams, which you can currently see on my screen. This is our spring 24 class, and there is nothing posted in general, but there is a little files tab up here. And if you click on the files tab up here, and Microsoft Teams will hopefully populate, there we go. You can actually find all of the videos that we posted for class. And then there's a little folder down here that says extra videos from Dr. Taylor. In extra videos from Dr. Taylor, some of these are just answering questions, yada, yada, but one of these says dealing with diprotic acids from March 6th. Dealing with diprotic acids, we'll go ahead and walk you through 2 ice tables and demonstrate why we just shortcut to using the Ka2 value for that second conjugate base. So it's there. Ta-da! So you don't have to think about it. You don't have to do it. But if you did want all of that beautiful math, highly recommend you check out this video that is in Microsoft Teams. It's already done. It's already recorded, and you can watch that one. I did that one before spring break because doing 2 ice tables out takes me about 20 minutes. And I just personally think we have better things to do in class. So it's already recorded, already done. The other problem was the book problem, talking about phenolphthalein. So the reason why I wanted to do this 1 second is 1, this is going to take some more math, but 2, I always like to talk about if we have a book problem, like why did we assign this book problem? So we assigned this book problem because something people don't often think about is indicators are acids and bases of their own accord. So that's why phenolphthalein has its own pKa, is because phenolphthalein is an indicator by itself. Then it's asking you for the ratio of non-ionized. So keep in mind, we sometimes call that non-ionized. We sometimes also refer to that as unionized is the other terminology you may very well see. Form of the indicator to the ionized form at pH 8. This, and I know the person asked for B, I'm going to get there. But the thing is that because phenolphthalein is an acid of its own accord, this is actually a buffer problem. So that's the first thing that you have to do is basically we're just going to wind up using Henderson-Hasselbalch to say, well, what is my ratio of the non-ionized form to the ionized form? So granted, in the Henderson-Hasselbalch equation, it looks like this. And we're just going to solve for that ratio as it is. So I want a pH of 8. My pKa is 9.1, and I can solve for my ratio from there. I did already go ahead and take a look at the key, so I am actually going to flip over there, mostly because I do also want to make certain that this is all making sense. Okay, so the log, that's what I was, so the other thing I want to double check in here is the book did go ahead and do what I thought they were going to do, which is, let me show you this. To me, this is, I mean, it's not wrong, it's fine. But basically what they're doing here is you do solve, the ionized form is A minus, because whenever we're talking about ionized versus unionized, these things look like this. Plus, so the thing on the left is the unionized. The thing on the right is ionized. So when we originally solved for Henderson-Hasselbalch, this ratio is what's in the equation. The textbook wanted it flipped around. It's really not a big deal to have it the other way. Really, I think they just flipped it around because oftentimes when we talk about ratios, we like beautiful whole numbers. So if you did the original, you would have gotten that A minus divided by HA should be equal to 0.079. And granted, it is me also trusting that the textbook did it correctly, which I should not trust. Yay, okay. So they did this, which technically is 0.079 over 1. And then because they decided that they wanted to flip the ratio, they decided that then if you are going to put the unionized over the ionized, that would be 1 over 0.079, which is how they got 12.6. So anyway, so that's part A, which was not actually what the person in the chat wanted to ask about, but figured we'd go ahead and do part A before we got to part B. So part B says if 2 drops of 0.06 molar phenolphthalein are used in a titration involving a 50 milliliter volume, what's the concentration of the ionized form, so the A minus, at pH 8? Assume that 1 drop is 50 microliters, 0.05 milliliters. And yes, that is one of those weird things that as a biochemist, you actually do wind up memorizing how much a drop is. By the way, question that definitely nobody asked. This drop size is more determined by things like how water cohesion works and water adhesion works. So you would actually, because I was definitely like, what do you mean a drop is 50 microliters? You guys are kidding me. It's not that even all the time. Oh, but it is. So granted, raindrops are different because raindrops run into each other on the way down. But if you are physically holding something and you try to drip a single drop of water from either your burette or even off of your finger, if you do succeed in dripping a single drop, that actually is pretty close to the volume every single time. Yay, physics. Also, gravity matters because cohesion, adhesion, and gravity. Anyway, what was the question? If 2 drops, okay. So honestly, I think that the beauty of this is because we still have this same pH and we're still talking about Henderson-Hasselbalch. The beauty of this is the pH of buffers does not change with dilution. So what we're saying here is when we solved for A, you just had a ratio. And that ratio could have been in moles, it could have been in molarity, whatever, it's all good. But now it's saying, cool, you're going to take drops of this 0.06 molar, here's 1 concentration, and then you're just going to add 2 drops into a much larger volume. what's the concentration? So you are going to calculate a new concentration, but this pH number is going to stay the same through this concentration and through its dilution, and you never have to recalculate pH because the pH of a buffer does not change with dilution. So believe it or not, the reason why part B is there is to force you to demonstrate that you never ever recalculate the pH, even though the concentration changes drastically. That's what's happening. That being said, let's go ahead and take a look at the math. You just can tell I'm not super thrilled. Because basically it's the same ratio. I just have to figure out my new concentration. So one of the things I need to know for my new concentration is I need to know my new volume. So here's my new volume. I can do this all in milliliters. So I'm going to have my final volume is going to be 50 milliliters plus 0.05 milliliters. We're just going to assume that all of these significant figures work and hang on to that. Oh, but I have 2 drops, don't I? 2 drops. Sorry, making that noise with my mouth was not helpful. 2 drops. Boom. There we go. Great. 0.05 times 2 is 0.1. So here's my final volume. So this is where I'm headed. Final volume. And my initial volume, as we already demonstrated, is 0.1. So we had an equation that we used, especially in Gen Chem 1, to deal with volume and concentration changing. And basically, if this is my initial volume, my 0.1 milliliter, and it has an initial concentration of 0.06 molar, I can put that equal. This is going to be M1V1 equals M2V2, but I am getting some of the things out of order because here's my volume on the left. There's my molarity on the right. It's going to be equal to 50.10 milliliters. And the beautiful thing with M1V1 equals M2V2 is as long as my units are the same, they can be whatever I want. So I will be solving for this in molarity because, again, whatever my unit is whatever my ending unit will be. So as long as everything matches, I can use whatever I want. So this is then 0.1 times 0.06. 0.006 is equal to 50.1x divided by 50.1. I get x is equal to 0.1231196. I am going to check on the key to see if I'm along the right thing. So this is the molarity of my phenolphthalein in the beaker at the beginning, and this should be all I should need to do. That's my total molarity of all of my phenolphthalein. What's it going to make me do? Yeah, is this how well, we're fine. Sorry, the reason why I am hemming and hawing a little bit is because this is my total amount. You know what, I would actually, let's just solve it the way the book did it and let's not reinvent the wheel. Oh, but I want to so bad. So badly do I want to do this a different way. Because basically what this is since this is the total, and what I know about, we can use either one of these numbers, but I guess we'll use the 12.6, is what I know is that my HA over my A minus is equal to 12.6 and 1. I am not going to do it the way the book did it, am I? So therefore, what I can do is keep on using my ratios and say that, what did the question want? Hold on, I still want the ratio? the concentration of the ionized form. And with the concentration of the ionized form at a pH of 8. So I need the concentration of this thing, the ionized form. That means that my total here for all of this should be 13.6, right? 12.6 plus 1 is 13.6. And that should be equal to my total, 1, 2, 3, 1, 1, 9, 7, 6, divided on the thing I'm looking for, x. So I basically started with one and went to another one, and we'll double check to see if I have outsmarted myself. 1, 2, 3, 1, 1, 9, 7, 6 is equal to 13. This, by the way, I'm using cross multiplication. So I'm taking the 13.6 times x and then the 1 times that other number down there. And essentially I get to do this because these are ratios. So this is comparing two things to each other. These are all about ratios. I'm going to put that in scientific notation because we're getting awfully small here. 8.8 times 10 to the negative 6. The thing on the left, the 1 and the 13.6 are in, nobody knows. Those actually could be in molarity, come to think of it. Because it's just the ratio. So that ratio can be in moles or molarity. The stuff on the right, my x, and this other number is definitely in molarity. So that's in molarity. Did I do it? It worked. I'm so pleased. So the way your book did it. Oh, why would you have done it that way? What? I'm very confused. So I'll show you why I'm confused about the way the book did it, and maybe you are also confused about the way. I mean, it doesn't really matter. It probably was just a thing with significant figures. So the thing that bothers me is your book ignored the addition of the 2 drops. This bothers me. And then your new molarity was 1.2 times 10 to the negative 4. Oh, I guess if I rounded, it would have been the same. I got, as I was, so this number in blue, if I rounded, it would have been 1.2 times 10 to the negative 4. That would have been the same. And then they solved it a different way. So the mathematics that they went ahead and used was basically, it's the same notion. I just used different logic tests essentially, because again, the total in here is the 1.2 times 10 to the negative 4. And when we talk about the ionized or the unionized minus, or sorry, the total is everything. So the total would be equal to, or in this case, the unionized plus the ionized is equal to the total. Your textbook went ahead and decided that the ionized would be Y because that is the thing that we're looking for. And then the total is that number we solved for, 1.2 times 10 to the negative 4. And then we basically had this other thing, the unionized. And essentially you can solve for the unionized with the information that we have. 1.2 times 10 to the negative 4 minus y. So basically they just went ahead and recreated the ratio with a little bit of algebra. And then they didn't show you any of those algebra steps, mostly because it gets messy. It's not that bad. You guys have done all of that algebra before, because that's the thing where you just have to distribute and you just have to do all of the things and not mess up any of the distributions, which is honestly the reason why I used the cross multiplication also because that was a beautiful example of why cross multiplication is used. Because then I don't have to do this and keep track of everything. Oh, look, I get the same thing, 1.2 times 4. What? Divided by 13? Oh, divided by 13.6. Plug in the correct number into the calculator and maybe we will actually get the right answer. 1.2 EE negative 4 divided by 13.6. Yep, I still get it. So either way works. You can either have thought about it my wacky ratio way, or your textbook is essentially just walking you through how to think about the total amount, the unionized, and the ionized form altogether. So really, it's just a way to get a little deeper into buffers. I'm still going to stand by what I said originally, which is really the point that I would take home from this to make sure that you're okay with is the pH of the buffer does not change with dilution. But hopefully that helps. Yeah, honestly, that part B of the math, I would really not worry about this at all. I would just worry about the part A was really lovely, by the way. Part A was great, solving for the ratio. I thought part A was lovely, and I also thought that the pH of the buffer not changing with dilution was also lovely. The math in part B I did not find to be lovely, and that's my opinion. Anyway, hope this helps. Have a great day.